Welcome to Lesson 7.5 Content Moderation System. Learning objectives. In this lesson, you'll build a high-speed, accurate content moderation system capable of filtering toxic, harmful, and inappropriate content at real production scale. The core architectural decision here is classification instead of generation, and that single choice unlocks a 10 to 100 times speed advantage over generative approaches. You'll apply the custom task heads from Module 6.5 and the extreme optimization techniques from Module 6.6, bringing both of those concepts together into a single deployable system. Budget about 90 minutes for this one. It's advanced, so having Modules 1 through 6 under your belt, especially 6.5 and 6.6, will make everything click. Project overview. Sys Judes Judentum project overview. Here's the scenario you're solving. A social media platform moderating 5 million or more posts every single day. Right now, human moderators review flagged content with a 24 to 48 hour turnaround. Inconsistent decisions depending on who's reviewing, and a $500,000 annual cost. Users are still seeing harmful content slip through. The target state is instant automated first pass moderation, under 100 milliseconds per post, 95% or better accuracy on policy violations, and a cost of $50,000 a year. That's a 10 times cost reduction. The expected impact: 90% less human moderation workload, 99% of content moderated within seconds, and $450,000 in annual savings. These aren't theoretical numbers, they're achievable with the architecture you're about to build. The success metrics are precise and non-negotiable. F1 score above 0.95, precision above 0.94 to keep false positives low. You don't want to wrongly silence legitimate users, and recall above 0.96 to catch the violations that actually matter. On the performance side, under 100 milliseconds latency per request, over 1 million posts per day throughput on a single GPU, and critically bias disparity across demographic groups must stay under 5%. That last metric isn't optional. A moderation system that enforces policy inconsistently across groups isn't just technically flawed, it's a liability. Architecture overview. Here's the architectural insight that makes everything else possible. Previous projects in this course use text generation. The model predicts tokens one by one until it produces an answer. Content moderation doesn't need that. You just need a label, safe or violating. By attaching a custom classification head directly to the transformer's hidden states, you bypass the entire autoregressive decoding loop. That's where the 10 to 100 times speed advantage comes from. One forward pass, one probability distribution, done. The pipeline flows like this. Raw post text comes in and gets tokenized into the format llama-3.2-3b expects. The model, fine-tuned with LoRa, processes those tokens and produces hidden states. Rather than decoding those hidden states into text, you aggregate them using either the CLS token or mean pooling across all token positions. That aggregated vector then passes through the classification head, which maps it to your output classes: toxic, hate speech, spam, and so on. The result is a probability distribution across those classes in a single forward pass. On top of that, you'll apply torch.compile for speed, mixed precision for memory efficiency, and batch processing for throughput. 2 Tesla P40S can handle this workload comfortably. The system classifies across 7 violation categories. Toxic and hate speech covers offensive language, slurs, and harassment. Violence and gore covers graphic violence and explicit threats. Sexual content covers NSFW and explicit material. Spam covers commercial spam, and harassment covers bullying, doxing, and targeted threats. Misinformation covers demonstrably false claims, though this one is context dependent and worth flagging for human review rather than auto removal. And self-harm covers suicide ideation and self-injury content, which requires careful handling given platform safety obligations. Each category has different threshold requirements, and you'll see how that plays out in the classification head design. Phase 1. Data collection. The data collection script does several things that directly determine whether your model is fair and accurate, not just whether it trains without errors. It starts by creating a project directory structure and loading 3 public datasets: toxic comments, hate speech examples, and safe content from Twitter. Each one covers a different slice of the real-world distribution your model needs to handle. Watch the print statements as each dataset loads. They confirm the data is accessible and give you a quick sanity check on record counts before you invest time in processing. The processing step categorizes toxic comments by severity, labeling each example as safe or violating. Then comes a step that most tutorials skip but that genuinely matters: balancing the dataset so safe and violating examples are equally represented. Class imbalance is one of the most common reasons moderation models fail in production. A model trained on 90% safe content learns to predict safe for everything and still achieves 90% accuracy on the training set while being completely useless. The script guards against that. Finally, it splits into training and validation sets, saves both as JSON, and runs a basic bias analysis to surface any demographic skew before you ever touch the model. Phase 2. Training with custom classification head. The training script is where the architecture comes together. It loads llama-3.2-3b-instruct from unsloth and applies LoRa, the same pattern you've used throughout this course, but now serving a classification task instead of a generative one. The custom classification head sits on top of the transformer. It takes the pooled hidden states, applies dropout for regularization, and maps them down to your number of output classes. Dropout here is doing real work. Without it, the small classification head overfits quickly given how much capacity the underlying transformer has. The tokenization step converts your training and validation text into model inputs, and the training configuration sets batch sizes, evaluation intervals, and learning rate schedules appropriate for a classification objective. After training completes, the evaluation block produces a full classification report and confusion matrix. The numbers you want to focus on are the false positive rate, flagging safe content as violating, and the false negative rate, missing actual violations. Those two error types have very different real-world costs, and the confusion matrix makes that trade-off explicit. Phase 3. Extreme optimization. Training gives you an accurate model. Optimization gives you a deployable one. The script loads your trained model and classification head with 4-bit quantization active. This cuts memory footprint significantly, which matters when you're running 2p40s and want headroom for large batches. The first optimization is torch.compile, which traces the model's computation graph and compiles it to optimized machine code. The warm-up phase that follows isn't just boilerplate. Torch.compile uses lazy compilation, meaning the first few inference calls trigger the actual compilation. Running warm-up passes before benchmarking ensures you're measuring steady-state performance, not compilation overhead. Dynamic batching is the second major optimization. Instead of processing one post at a time, the batched moderator class accumulates requests and runs them through the model together. The throughput gains here are significant because GPU utilization jumps from maybe 20% on single requests to near full utilization on batches. The benchmark output tells you exactly where you stand: single request latency, batch throughput and posts per day, GPU memory consumption, and accuracy on a validation sample. You're looking for sub 100 millisecond latency and over 1 million posts per day. If either number is off, the benchmark output points you directly at which bottleneck to address. Phase 4. Production API with multi-GPU serving. The fast API application wraps everything you've built into a production-ready HTTP service. Incoming requests carry a list of texts and a confidence threshold. That threshold is the caller's way of saying how certain the model needs to be before flagging something. The moderation function processes those texts in batches, returning for each one a safety verdict, a confidence score, and a recommended action. That recommended action is important. High confidence violations trigger automatic removal, medium confidence results route to the human review queue, and everything else gets approved. You're not replacing human judgment, you're directing it to where it's actually needed. The response payload includes total processing time for the batch, which feeds directly into your SLA monitoring. The health check endpoint at startup confirms the service is running and reports GPU availability. When you see that endpoint respond with both GPUs detected, the system is ready to accept traffic on port 8000. Results and bias monitoring. The results hit every target. F1 score of 0.96 against a target of 0.95. Precision of 0.95 against 0.94. Recall of 0.97 against 0.96. Latency of and throughput of 1.9 million posts per day on a single Tesla P40. Nearly double the 1 million target. Every metric is in the green. Notice that latency and throughput both exceeded their targets by a wide margin. That headroom is what gives you confidence the system holds up under real production load spikes. The business impact is equally concrete. Operating cost drops from $500,000 to $50,000 per year, a 90% reduction. Review time collapses from 24 to 48 hours down to under 1 second. The platform now has capacity for 5 million posts per day on a single P40, with your second GPU available for redundancy or additional workload. And policy enforcement becomes fully consistent. The model applies the same rules to every post, every time, without fatigue or variance. Key takeaways. A wise 5 things to carry forward from this lesson. First, classification beats generation for moderation tasks by 10 to 100 times. Always reach for a classification head when you don't need generated text. Second, the custom classification head is the architectural keystone. Without it, you're leaving most of your speed advantage on the table. Third, optimization stacks multiplicatively torch.compile, dynamic patching, and 4-bit quantization together deliver a 3 to 5 times speedup over any single technique alone. Fourth, bias monitoring isn't a nice to have. Regular demographic audits are what prevent your system from enforcing policy unevenly across user groups. Fifth, balanced training data is the foundation everything else rests on. No amount of optimization fixes a model trained on skewed labels. This system is production ready. Next up is lesson 7.6, where you'll integrate and deploy everything you've built across this module. The moderation taxonomy diagram maps out the full classification space your model needs to cover. At the center is content moderation itself, branching into 6 violation categories and 1 safe category. Hate speech and harassment sit on one side, both focused on harmful interactions between users. NSFW content and spam occupy another branch, covering explicit material and unsolicited commercial content. Violence and threats, misinformation, and finally safe or benign content complete the picture. What this diagram makes clear is that safe is just one of 7 categories, not the default. Your model needs to actively recognize safety, not just fail to find a violation. Keep this taxonomy in mind as you review your training data. If any category is underrepresented, your model's recall on that category will suffer first. The detection pipeline diagram shows how automated and human review work together rather than in isolation. User content enters a fast classifier first, reg-s patterns, and rule-based checks that can make an instant determination on clear-cut cases. Clear violations get actioned immediately. Clear safe content gets approved. The interesting cases, the ones where the fast classifier is uncertain, flow to the fine-tuned moderation model for deeper analysis. That model produces a confidence score, and the score determines the routing. High confidence approves or removes automatically. Medium confidence sends to the human review queue. Low risk gets approved. This tiered approach is what makes the economics work. You're not running the full model on every post. You're reserving it for the cases that actually need it, which keeps latency and compute costs in check. The escalation flow chart shows action distribution broken down by violation category, auto removed, sent for human review, and approved after review. Hate speech and harassment show the highest auto removal rates, which makes sense. These categories tend to have clear linguistic signals the model can identify with high confidence. NSFW content and spam shift more toward human review, reflecting greater ambiguity in those categories. Violence and misinformation show the most nuanced distribution, with a meaningful fraction requiring human judgment. What this tells you practically: if you're seeing too many false positives in a category, your confidence threshold for auto removal in that category is too low. If you're seeing too many misses, it's too high. The per category breakdown gives you the granularity to tune those thresholds independently rather than applying a single global cutoff. The precision recall trade-off chart is one of the most practically useful outputs your evaluation pipeline produces. As the classification threshold increases, both precision and recall change, but not at the same rate. The blue precision line rises as you increase the threshold, because you're only flagging content the model is very confident about. The orange recall line falls, because higher confidence requirements mean more violations slip through. The green F1 line balances both, and it peaks at a threshold of 0.36. That vertical dashed line marks your optimal operating point for this model. The key insight is that this threshold is empirically determined from your validation data, not guessed. For content moderation specifically, you'll often want to shift slightly left of the F1 optimum to prioritize recall, accepting a few more false positives in exchange for catching more real violations. Where exactly you set that threshold is a product decision, not a technical one. But now you have the chart to make that conversation concrete.